Okay, this chapter is on thermal energy, which you might also call heat energy, and thermodynamics. And there are going to be two real main concepts that we're going to talk about: heat and temperature. And a lot of people tend to mix those up. They think that they're the same thing, but we're going to see that heat and temperature are actually different ideas, and we're going to see how we can make use of both of them to understand a lot of different phenomena in nature. So, over the course of this chapter, we're going to be talking about temperature, and we'll talk about how you can have an absolute zero of temperature. And then we're going to talk about heat, which is different from temperature, although we'll see that the two are related. They are not exactly the same thing. We'll talk about how you can deal with a quantity of heat, and that'll lead us to developing the so-called laws of thermodynamics. And this really gets at the heart of how heat works in our universe. And one of the laws of thermodynamics deals with the concept of entropy, which is very important. And then we're going to talk about some different effects of these rules, including the idea of specific heat capacity, thermal expansion, and particularly the expansion of water, which is kind of strange, but the fact that it's strange makes it kind of interesting. Okay, the first concept we're going to talk about is the idea of temperature. And so, temperature is a number that corresponds to the warmth or coldness of an object. And we know that temperature is measured by a thermometer. And what's maybe not clear is temperature is an example of something that's called a per particle property. And we'll talk about what that means in just a second. But one of the things that's interesting is that temperature has no upper limit, but there is a definite limit on the lower end. We're going to see that there's a temperature called absolute zero, and it's impossible to get colder than absolute zero. However, there's no upper limit on temperature. You could have 1,000,000 degrees and then have 1,000,001 degrees and 1,000,002 degrees or 10,000,000 degrees or 100,000,000 degrees. There's no limit to how hot something can be, but there is a limit to how cold something can be. Now, this business of a per particle property, that's going to come into play when we see what the actual definition of temperature is. So we can talk about the actual definition of temperature, and it's really right in here. Temperature is proportional to the average translational kinetic energy per particle in a substance. Well, that's a mouthful, and it's a little bit confusing, so let's break down what that means. First of all, let's remember that kinetic energy is 1/2 the mass times the speed squared, and so that's what the kinetic energy is. And so when you have a substance, you have and it can be a box that's filled with gas or filled with a liquid like water, or it could even be filled with a solid, like you could just fill it up with sand or whatever. You have all this stuff in here. When you zoom in on your stuff is made up of atoms and molecules. And those atoms and molecules at the microscopic level, they're moving back and forth. And so each atom has a mass, and each atom has a speed as it's moving back and forth. And so every atom has a kinetic energy. And so if you take the average kinetic energy of all the particles that make something up, all the atoms, all the molecules, all of their motion, each atom has a certain amount of kinetic energy. If you take the average amount of kinetic energy over all the particles, you'd have so much energy per particle, and that is what gives rise to the temperature. Practically what this means is that things that their atoms and molecules are vibrating back and forth faster, they have a bigger or a higher temperature. And things that are moving more slowly, they have a lower temperature. Now, practically when we're talking about the motion of the atoms and molecules of a substance, we know that most substances are broken down into either a gas, a liquid, or a solid. And so we can see what that means in terms of the motion. The gas is going to be moving, if you've got gas in a box, the atoms of the gas, the molecules that make up the gas, are going to be bouncing around in the box, and that's how they're moving. If you have a liquid, so my box is filled with liquid, the particles in the liquid, they're going to be sliding past one another, jiggling back and forth. And then in a solid, the thing about a solid is that the atoms and molecules are fixed in their positions. They're not allowed to move around, but they can vibrate back and forth, and that's what happens. And up here on the right, you can see the three different ways that a molecule can move. It can undergo what's called translational motion, so that means it can just zoom back and forth. It can also rotate or spin, that's called rotational motion. And then the atoms that make up the molecule can vibrate back and forth, and that's called vibrational motion. And those are the three kinds of motion that can occur when something has temperature. The atoms, the molecules, they can translate, they can rotate, and they can vibrate. Now, thermometers are what are used to measure temperature. And basically, a thermometer works by having some property that you can measure that changes with temperature. And so you measure how that property changes, and you can calibrate it to read different temperatures. The most common type of thermometer is one that uses expansion or contraction of a liquid. And usually the liquid in the thermometer is mercury. So if the liquid inside your thermometer looks silver, it's probably mercury. And if it's red or some other color, it's probably some kind of colored alcohol. Usually they use red. Now, just FYI, if you have a mercury thermometer, that's actually pretty dangerous. That's why you don't see mercury thermometers used as much today as they were in the distant past, because if the thermometer breaks and the mercury spills out, it's incredibly poisonous. And so you want to avoid using mercury thermometers if you can, and that's why most thermometers used today that have this kind of style with the expansion or contraction of a liquid, they use the colored alcohol. Now, the way a thermometer works is you put the thermometer, if I've got a thermometer and I'm boiling water and I want to measure how hot the water is, I put the thermometer in the water, and the heat energy transfers from the water into the thermometer, and that causes the alcohol in the thermometer to expand up the tube, and there are little divisions on the tube that you can read numbers off of to read the temperature. But really what's going on is the heat has to flow from the water into the thermometer to make that alcohol expand. And so the alcohol will keep expanding until the thermometer and the water are in what's called thermal equilibrium. And that means that they have the same average kinetic energy per particle, or that's a fancy way of saying the same temperature. Now, there are other kinds of thermometers that use other physical properties. There's a property in electrical circuits called electrical resistance, and there are thermometers that work by passing a current through a wire, and if the resistance changes, they can tell you what the temperature is that way. Another kind of thermometer, though, is what's called an infrared thermometer, and they actually operate by sensing the infrared radiation. Every object that has temperature is radiating electromagnetic radiation. The sun is very, very hot, and very, very hot things like the sun tend to radiate a lot of visible light. Things like us, people, we're not as hot as the sun, but we are still radiating energy, and what we radiate is what's called infrared radiation. Now, that's invisible to our eye, but there are detectors that can detect the infrared radiation. If you've ever seen the Predator movies, the Predator had kind of vision that would let him see heat. He could see the infrared radiation coming off of things. We see visible light, but there are machines that can detect infrared light. And by measuring how much infrared light's coming off of an object, you can tell what its temperature is. And so that's how infrared thermometers work. Now, one of the advantages of an infrared thermometer is that you don't actually have to touch the thing whose temperature you're measuring. And so that's quite useful. Now, here's a picture of a thermometer, and the idea is you've got this colored alcohol in this glass tube, and when the thermometer heats up, the glass tube will expand a little bit, but it actually doesn't expand nearly the same amount as the alcohol. And so as the alcohol expands, it rises up the tube. And the hotter the temperature of the thermometer, the higher the alcohol rises. And of course, the thermometer is calibrated so that you can read off the thermometer scale what the temperature is. I'm sure all of you have seen thermometers before and know how to use them. And you've probably learned before that there's two main scales that are used in the world. One of them is called the Celsius scale. And on the Celsius scale, the thermometer goes from 0 to 100 degrees, And these are the 2 points for freezing water and boiling water. Now, on the Fahrenheit scale, those same 2 points for freezing water and boiling water, they're 32 degrees and 212 degrees. And so we can summarize that here. On the Celsius scale, you have 0 for the freezing point of water and 100 degrees for the boiling point of water. On the Fahrenheit scale, you have 32 for the freezing point of water and 212 for the boiling point of water. That's how you create the scale. And in most countries in the world, they use the Celsius scale, and it's an international scale that's used in science. So almost always in science, you'll see temperatures measured on the Celsius scale. The Fahrenheit scale is an older scale, and it's still used in the United States, but it's not used in many other places. So if you ever travel to another country, you'll have to get used to seeing temperatures on the Celsius scale, which can be quite different. And so, when you're at 100 degrees, that's not even 40 degrees on the Celsius scale. 100 degrees Fahrenheit is not even 40 degrees on the Celsius scale. So the numbers that you get for different temperatures are quite different using those scales. One thing that you may not have heard about before is that there's actually a very common third temperature scale that's used almost exclusively in science, and that's called the Kelvin scale. And that was named after Lord Kelvin, and it uses 273 Kelvin for the freezing point of water and 373 Kelvin for the boiling point of water. Now, the reason that we have a Kelvin scale is the Kelvin scale is based on absolute zero. And so absolute zero occurs at minus 273 degrees Celsius, and we're going to talk about what that means in a sec. But I can also note that the Celsius degrees have the same size as the Celsius degree. There's 100 degrees between the freezing point of water and the boiling point of water on the Kelvin scale. And so that's the same. So the Kelvin goes from 273 to 373. There's 100 degrees between those 2 points. The Celsius scale goes from 0 to 100. There's 100 degrees between those 2 points. So the degrees have the same size. But the difference is that the Kelvin scale has an absolute zero of temperature. Now, what that means, we know that temperature is caused by atoms and molecules moving. They're either vibrating back and forth, or they're translating, or they're rotating. There's some kind of motion for these atoms and molecules. And the faster they're moving, the hotter the substance is. What that means conversely is that the slower they're moving, the cooler the substance is. So as something cools down, the atoms and molecules will be moving slower and slower. What's the slowest that they could possibly move? That would be when they stop. When they stop moving, you can't possibly get any colder than that. Because what would that mean? It wouldn't mean anything. So absolute zero is the temperature when all the atoms and all the molecules of a substance stop moving completely. As we'll see later, you can't actually ever get to that temperature. There's always going to be some motion. But in theory, if you could stop the motion of the atoms and molecules of a substance, its temperature would be what we call absolute zero. And that's the coldest temperature that you could possibly get to in our universe. Now, just to recap what we have, we said that temperature is the average kinetic energy of all the particles in a substance. And so, what's heat then? Or what is thermal energy? Thermal energy, or heat energy, that's the total energy, both the kinetic and the potential energy of all the submicroscopic particles that make up the matter. And this ties into what's called the kinetic theory of matter, and that's the idea that matter is made up of tiny particles, and that's atoms or molecules, that are always in motion. The word kinetic means motion, like kinetic energy is the energy of motion. Well, kinetic theory of matter is the theory that matter is made up of moving tiny microscopic particles. And then we can talk about the temperature as being the average kinetic energy of those particles. And then the thermal energy, or the heat energy, is the total energy of all those particles. Now, we talked about absolute zero, which is, of course, the lowest limit of temperature. That's the coldest that something can be. And that's the temperature in which all atoms or molecules have lost all their available kinetic energy. So basically, all the atoms and molecules have stopped all their motion. And so that's the coldest temperature that you can be. And this chart just kind of shows sort of variations of different possible temperatures in both Celsius and in Kelvin. And you can see we go up. As you go up, you can see water boils at 100 Celsius. As you go up hotter, you can get at 1800 Kelvin. Iron melts. The sun has a surface temperature of 6000 Kelvin. A really hot star would have a temperature of 50,000 Kelvin. The center of the sun is 20 million Kelvin. And if we were to detonate a nuclear bomb, a hydrogen bomb, the temperature in that detonation would actually be 100 million Kelvin. So the temperature gets very, very hot very fast. Now here's an example that's very interesting, considering the thermal energy in a sparkler. A sparkler burns very, very hot. The fact that it's giving off visible light means that it is literally thousands of degrees. In fact, we can see that the temperature of the sparks of a sparkler are about 2,000 degrees Celsius. That's about 3,500 degrees, 3,600 degrees Fahrenheit. So it's very, very hot. And yet, you can hold a sparkler without getting burned. Why is that? Well, in each of the sparks of the sparkler, there is a lot of energy per molecule of the spark. But the total energy in the whole sparkler is very small because each little spark only contains a few molecules. And so while the energy of those particular molecules are very, very high, hot enough to burn bright, the sparkler itself is not that hot because only a few molecules are that hot at a time. And so the energy is relatively low, even though the temperature can be quite high. Now we have an official definition of temperature. It's the average kinetic energy per particle in a substance. Heat is defined as a flow of thermal energy due to a temperature difference. And so thermal energy will flow from one material into another material, and the amount of thermal energy, and remember the thermal energy, that is the total energy, both potential and kinetic, of all the particles that make up a substance. That energy can flow from one object to another, and that energy flow is called heat. Now, the natural direction of heat flow is from a higher temperature substance to a lower temperature substance. It's never going to spontaneously go the other way. And so that's one of the rules of nature. So imagine I've got two pots that have water in them, and one pot has 3 times as much water as the other, and I put in on my stove the same amount of heat into each pot. What's going to happen? Well, this pot is going to get all of that heat into a smaller amount of material, and so the temperature, the average motion of all the atoms and molecules of this liquid is going to increase much more because that heat energy is distributed among fewer particles. And so the energy per particle is much higher. The temperature in the bigger pot is going to be much lower because that energy is spread out over a bigger number of particles. Now, to get this guy up to the same temperature, if there's 3 times as much liquid, it's going to take 3 times as much heat to give you the same temperature. So that is kind of an interesting thing. Next, we want to talk about the units for energy. Heat is energy in motion. It's the transfer of energy. So remember that, if something is just sitting there, it doesn't have heat. Heat is what transfers from one object to another. And so only through the process of transfer do you have heat. And it's this transfer of thermal energy. So what are the units of heat? It turns out that the units of heat are generally joules, which is the very common unit for energy. We've seen joules before for potential energy and kinetic energy. And so we know that the temperature of something is the average kinetic energy, and kinetic energy is measured in joules, so it makes sense that heat could be measured in joules. But there's also a more common unit for heat, and that's called calorie. And that's kind of like having feet and meters be different units for length. So joules and calories are different units for heat energy. And you can, of course, convert from one to another. The way you convert is actually right here. You can say that there are 4.19 joules for every calorie. And what is a calorie, though? A calorie is the amount of heat, it's defined as the amount of heat needed to raise the temperature of 1 gram of water by 1 Celsius degree. So that's how many calories of energy are needed to do that. And so if I've got a gram of water, so I've got a little mass of water, and it's 1 gram's worth of water, and I put heat energy into that water, I heat it up. How much heat energy is going to be needed to heat that gram of water by 1 Celsius degree? And it turns out that it's either going to be 1 calorie or 4.19 joules. That's the amount of heat that will change the temperature of 1 gram of water by 1 degree. Now, calories are particularly used when rating food or fuel. And so if you eat a banana, say, how much energy is available in that banana to power your body? And basically, we measure that by measuring the amount of energy that are released when those foods are broken down. When that banana goes in your stomach and gets broken down by your body, energy is released. How much of that energy is released? And we generally will measure such energy releases in a unit called a kilocalorie. And you might remember from previously that a kilo is a prefix that means 1,000. And so a kilocalorie would be 1,000 calories. Just like a kilometer, a kilometer, a kilometer is 1,000 meters. Well, a kilocalorie is 1,000 calories. But here's what's really weird. 1 kilocalorie is sometimes called 1 calorie with a capital C. In other words, 1 calorie with a capital C is equal to 1,000 calories with a little c. And that's kind of confusing, but that's just the way they do it. I don't know why. They didn't ask me. I'd have told them not to do it that way, but that's just how they do it. So if you see the word calorie and it has a capital C, it's actually a kilocalorie. And that's usually the kind of calorie that you're talking about when you say this muffin has 600 calories. That's how much energy is available for your body to use when you digest that muffin. Now, if a calorie is the amount of energy needed to raise a gram of water by a Celsius degree, a kilocalorie would be the amount of heat energy needed to raise the temperature of a kilogram of water by 1 Celsius degree. And so it's just a different definition of heat, but little calories tend to be used in scientific contexts, and big C calories tend to be used when you're talking about food or fuel. So here is a little question that we can test our understanding with. So imagine that you heat up a half a cup of tea and its temperature raises by 8 degrees Celsius. How much will the temperature rise if you add the same amount of heat to a full cup of tea? So we've got a cup of tea here, and it's filled halfway up with tea, and we put it on the stove and we heat it up, and we raise the temperature of a half a cup of tea by 8 degrees Celsius. Now, if I take another cup of tea and I put in the same amount of energy, but it's a full cup of tea, how much will the temperature rise? Well, if I've got twice as much stuff, but the same amount of energy, the amount of energy per particle is going to be cut in half, and so the temperature is only going to go up 4 degrees Celsius. And so if you put the same amount of heat and you get double the amount of stuff that you're applying that heat to, you only get half the temperature rise.